Let's jump right in. Welcome to this explainer, where we're tackling something I know keeps every senior software architect up at night: system performance. But look, we're not just trading isolated coding tricks today. We're talking true, full-stack performance engineering. We're going to evaluate the entire system stack, literally from the database foundation all the way out to the mobile edge, and piece together a highly resilient architectural blueprint for 2026.
So let me ask you this right off the bat. Where is your system's true bottleneck? You might immediately think, oh, it's my database queries, or maybe it's that massive JavaScript payload. But honestly, the real bottlenecks almost always hide in the seams of our architecture. Just consider this pretty stark reality from our sources. 53% of users will literally abandon a mobile app if it takes longer than 3 seconds to load. 3 seconds! If your architecture isn't optimized from the absolute ground up, you aren't just losing milliseconds, you're actively failing your core business metric.
Okay, here's our game plan. We're taking a methodical, bottom-up journey through the tech stack today. We'll start with high-speed database seeding, then move up to the HTTP/3 network revolution, tackle optimizing front-end and assets, look at mobile network resilience, and finally bring it all together with our full-stack synthesis.
Section 1. High-speed database seeding. This is the absolute foundation of developer velocity.
As an architect, you already know that having a blazing fast front end is, well, completely useless if your dev team is sitting around bottlenecked by hours of manual database resets. Empty databases just kill productivity, and slow resets mean starting over from scratch every single time. So let's look at the data layer. The legacy approach, it relies on row-by-row inserts. Those fire off individual transactions, trigger model events, and run validations for every single record. It's incredibly inefficient. The modern architectural approach, though, uses bulk ingestion. By relying on idempotent operations, meaning you can run them repeatedly without changing the end result beyond that initial application, like an upsert or create many, you can safely batch these inserts without throwing any constraint violations.
And the performance difference here is just staggering. By ditching those individual queries in favor of bulk inserts, using native upsert all methods in frameworks like Rails or create many in Node environments, you can hit a massive 9.4x speed improvement. A process that used to take minutes literally drops to mere seconds. That's not just a minor tweak, that's an immediate return on your architectural investment that completely unblocks your engineering team.
Now you might be wondering, what if we're ingesting massive data sets? We're talking data sets exceeding several million rows. In that case, even a good ORM's bulk insert might choke. That's where the staging table pattern comes into play. It's pretty much the absolute gold standard for high-speed ingestion. Step 1, you bulk load your data into a temporary staging table that has 0 indexes and no foreign keys. Step 2, you build those indexes after the data is fully loaded. Why? Well, because building indexes during a load forces your database to perform some really expensive tree rebalancing on every single insert, which completely destroys your performance. And finally, step 3, you perform a direct server-side move to the production table using a merge statement. This keeps your CPU from bottlenecking and shifts the heavy lifting over to disk I/O, which is highly parallelizable.
Moving on to Section 2, the HTTP/3 network revolution. Time to overhaul that transport layer.
Okay, so our data layer is sorted out. Now we face the next big architectural battle. Because let's face it, no matter how fast your database is, network latency is still the most significant bottleneck for modern apps. The crucial piece of the puzzle here is understanding the massive shift from TCP to QUIC. HTTP/3 basically throws the legacy TCP protocol out the window in favor of QUIC, which is built on UDP. Since UDP is connectionless by design, it completely avoids TCP's fatal flaw, head-of-line blocking. You know how in TCP, if just one single packet drops, the entire connection stalls waiting for a retransmission? Yeah, QUIC doesn't do that. It manages data streams independently, so a lost packet only affects its own specific stream, letting the rest of your app's data flow uninterrupted. Oh, and it comes with TLS 1.3 encryption baked right in by default. It's a total game changer.
The real-world impact of this is undeniable. Traditionally, TCP and TLS take about 2 to 3 full round trips just to establish a connection. HTTP3 slashes that down to 0 or maybe 1 round trip. For returning users, your data can literally be sent immediately. Plus, because QUIC uses connection IDs instead of IP addresses, network migrations happen seamlessly. So if a user walks out their front door and switches from Wi-Fi to a cellular network, the connection doesn't break. There's no forced rehandshake. The whole shebang stays connected. Overall, rolling out HTTP3 can cut your page load times by up to 30%.
Section 3. Optimizing front-end and assets. Let's talk about mastering client delivery. This is the layer where we tackle the visual and interactive elements your user actually downloads and executes. Think about it. Images often make up 50 to 70% of a page's total weight. For a modern 2026 architecture, formats like JPEG and PNG are strictly legacy fallbacks. The data proves it. WebP gives you a solid 35% file size reduction over JPEG. But AVIF, which is based on the incredibly efficient AVI video codec, it frequently shrinks file sizes by 50% or more, all while keeping the fine details perfectly crisp. Serving AVIF files through the HTML picture element will drastically improve your largest contentful paint, which, as we know, is the core metric for how fast the user actually perceives your page loading.
But hey, asset optimization isn't just about shrinking images, right? It's about wrangling your JavaScript execution. Those massive monolithic bundles just block the main thread and cause really frustrating UI lag. To fix bloated JS, we have to enforce some strict architectural rules. First, you've got to implement route-based code splitting using dynamic imports. Honestly, doing just that alone can slash your initial bundle sizes by 60 to 80%. Second, start utilizing tools like the React compiler for automatic memoization to stop those expensive, unnecessary component re-renders. Third, apply aggressive tree shaking at build time to mercilessly eliminate dead code. And finally, if you've got really heavy CPU computations going on, offload them. Move them off the main thread and into background web workers. Your UI simply must remain instantly responsive.
Section 4. Mobile Network Resilience. We're pushing out to the edge.
So we've optimized the backend, we've tuned the network, and we've shrunk the client payload. Awesome. But now we have to face the brutal reality of mobile environments. Users are constantly fluctuating wildly between blazing fast 5G and absolute dead zones. I want you to let this metric really sink in for a second. 60% of users will uninstall an app immediately after encountering repeated crashes or errors. Systemic mobile optimization is not just a technical nice-to-have anymore. It is a non-negotiable bottom-line issue, because if your app can't handle a spotty network gracefully, you're going to lose that user forever. So how do we, as senior architects, actually solve this? We do it through dynamic mobile load balancing and highly intelligent resource allocation. Here's the playbook. Step 1. Bundle and batch your non-urgent requests. This cuts down on those battery-draining radio state transitions on the user's device. Step 2. Apply adaptive prefetching. Your application absolutely needs to detect the current network generation. You should be prefetching aggressively if they're on 5G, but behaving highly conservatively on 3G to save their bandwidth. Step 3. Leverage AI-driven capacity planning. Modern edge architectures are starting to use predictive models like long short-term memory networks, which analyze time series data to forecast traffic patterns. By building AI digital twins, which are basically virtual simulations of your network conditions, architects can adjust load balancing in real time, hitting resource efficiency levels of nearly 99%. It's incredibly powerful stuff.
Section 5. The Full Stack Synthesis. This is your 2026 blueprint.
We have covered some immense ground today, and right here is your tactical, enterprise-grade roadmap. For the database, stop those row-by-row loops, move to bulk ingestion, and enforce strict connection pooling. For the network, enable HTTP/3 and QUIC at your load balancer to finally eliminate head-of-line blocking once and for all. For the front end, make the switch to AVIF formats and implement those dynamic JavaScript imports to really slash your bundle sizes. And for your longer-term strategy, look into integrating AI-driven predictive cache warming into your CI/CD pipelines. That ensures your system is proactively ready for high-priority user traffic before it even hits. Remember, optimizing at every single millisecond is how you build a highly resilient, globally scalable system. As we wrap up, I want to leave you with a final, somewhat provocative thought. Take a really close look at the systems you're managing right now. Is your current tech stack truly built for 2026 scale? Or are you just applying expensive band-aids to legacy bottlenecks? I highly encourage you to challenge yourself and your team to audit your architecture against these principles. Thank you so much for joining me on this explainer. Keep learning, keep optimizing those stacks, and I'll see you next time.